Hello everybody. I welcome you all to NCAS Geology class. Today I'll discuss about the interior of the earth or internal structure of the earth. We know earth is a planet of the solar system and it is a spherical body which is having a radius of 6371 kilometers. So to know the interior of the earth, it is not possible to collect the material from the entire earth, from the surface up to the center of the earth, and study the material and know of what material the earth is made up of. So, the information that is available regarding the interior of the earth are all based upon indirect evidences, indirect methods. So, we can discuss the interior of the earth on the basis of these two methods, direct method and indirect method. Direct method is only possible to certain depth, up to which human interference can be possible. For example, through deepest mines. If we take into account the gold mines of South Africa, it goes to a depth of 3 to 4 kilometers. So up to 4 kilometer depth, we know what material are there within the earth and how they are being placed. Similarly, if we take into account the deep ocean drilling at the Arctic Ocean, that goes to a depth of 12 kilometers. So up to 12 kilometers we can know what is the material of the earth and how they are being placed. Similarly, volcanic eruptions provide the data about the composition of the earth's interior because magma from earth's interior is coming up to the surface of the earth and which is accessible to our study. So, but in that case, we cannot be sure with regard to the depth from which that material is being pulled or that material is coming through eruption. That's why, but we can be sure with regard to the composition of the earth's interior or the melt composition, which is the composition of solid crust, solid rocks which have been melted and the magma has been produced out of the melt of rocks. So what might be the composition of the rock types within the earth interior? That can be known from the volcanic eruption. Similarly, meteorites. Meteorites are the extraterrestrial bodies which are falling onto the surface of the earth every now and then, and there are some meteorites which are very big in size and they are found to fall to the surface of the earth, and all other meteorites are found to be burnt in the atmosphere because of the friction with the earth's atmosphere, and they are found to be totally burnt before they touch the surface of the earth. So meteorites actually they represent one planet which has been broken and is forming asteroids between Mars and Jupiter, and that from that region the small planet matter are falling onto the surface of the earth, and these are called meteorites. And if you take into account the composition of the meteorites, they belong to siderites or iron meteorites, siderolytes or iron sulfides, aerolites or stony meteorites, or tektites or silica glass. So these four types of meteorites are falling onto the surface of the earth. And as it represents a broken planet, their composition must be equal to the composition of the Earth's interior. And that is generally assumed that Earth is composed of iron, Earth is composed of iron sulfides, Earth is composed of stony meteorites. So these are the evidences which are presented by the meteorites, by our probe into the oceanic crust through drill holes, or our entry into the mines up to maximum 4 kilometers. That knowledge is the direct knowledge about the Earth's interior. So all the evidences that we know about the Earth, which is a big sphere having radius about 6371 kilometers, such a great depth, such a great distance. So regarding that, whatever information we have got, they are all based upon indirect evidences. So what are those indirect evidences? It is rise of temperature. If we look at the crustal rocks, the rise of temperature is more in the crust because the geothermal gradient is high because of the concentration of the radioactive elements in the crust, and that's why crust shows a high temperature gradient, and it is about 25 degrees centigrade per kilometer. But at this rate, this temperature is not rising with depth. If this would have been the case, then maximum temperature, that is about 25,000 degrees centigrade, should have been at a depth of 2900 kilometers. So at this temperature, most part of the earth would have been melted, but that is not the case. So temperature is not rising in that rate as it is rising in crust. And if you take into account the depth at which rocks melt, it can be said that the 100 kilometers depth is a normal depth where the rocks can be melted, because at that depth the temperature can be around 1100 centigrade, and at this temperature rocks can be melted. And as you know, the material that is coming from the Earth's interior in form of magma, that generally comes below this 100 kilometer depth, and the temperature of the magma that is observed on the surface, that generally goes around 1100 centigrade. That's why we can say that temperature of the earth is around 1100 centigrade at 100 kilometer depth, and it is about 6000 degrees centigrade at the earth's core, which is at a depth of 6371 kilometers. And this temperature is equal to that of the outermost temperature of the sun, because earth is derived from the sun. So we can say that Earth's crust is made up of light materials along with radioactive elements, and as the radioactive elements are not there within the core, so these are represented by sulfides and heavy silicates, and in the core there must be nickel and iron, which are totally devoid of radioactive elements, and temperature is slowly rising with depth. That's why temperature goes to 6000 degrees centigrade at the core. Beside this temperature rise, we have the density. If we take into account the density of the earth, it is around, the average density of the earth is about 5.5 gram per centimeter cube, and if you take into account the composition of the density of the crustal rocks, it is around 3. So it is expected that the center of the earth must be made of very heavy rocks or heavy metals having density more than 11 gram per centimeter cube, so that the average density of earth can come to 5.5. And that is actually the case. Interior of the earth is made of nickel and iron. Then besides it, we have the value of G. G value of the gravitational value of earth is found to change from point to point on the earth's surface. It is maximum in the poles and to some extent low in the equator, because it is related to the earth's radius. Equatorial radius is more than that of the polar radius. And besides that, the presence of heavy rocks at the subsurface and presence of light rocks at the surface or subsurface, that controls the value of G. And deviation in the value of G on the surface of the earth is interpreted in terms of gravity anomaly. So gravity anomaly is presented because of the presence of light rocks and dense rocks. Near dense rocks, the gravity anomaly will be positive. Near light rocks, it will be negative. And it has been seen in case of or nearer the Himalayan region, it has been seen that the gravity value is lower compared to the average value or the normal value of G at some distance away from the Himalayas. So near the Himalaya the value is low because the Himalayan rocks are made up of very low density rocks, and it is also having a deep root which goes to a depth of about 80 kilometers. Himalayan zone is having a root which goes up to 80 kilometers, and it is made up of light rocks. Light rocks forming the hill mass on the ground, and it is having a root, deep root, having depth 80 kilometers. It is about 9 kilometers. Maximum height can be Mount 9 kilometers. It is the height of Mount Everest. So, because of the presence of these light rocks, the value of G is becoming lower. So, the value of G can give some information about the type of composition of the Earth's interior. So, here the composition is light rocks. And over the mid-ocean areas, the G value is, in the mid-oceans, the value of G is presenting positive anomaly or high value of G. That is because it is made up of dense rocks. So, the composition of rocks throws or gives or modifies the value of G, and on the basis of value of G, it is possible to get some information about the Earth's interior. So, beside that, we have the magnetic field of the Earth. Earth behaves like a giant magnet because of the presence of the liquid iron core, which is in the process of circulation. The circulating or convection current that exists in the interior of the core with iron, that is responsible for formation of a big, that behaves like a big giant bar magnet. So Earth behaves like a bar magnet. It can be possible because of the presence of the liquid iron core, where this iron is behaving like a geodynamo effect, because of which the Earth is presenting this magnetic field, and magnetic field is found to change its normality with time. Sometimes it becomes normal north, it becomes south, and in some time it becomes south, it becomes north. That is change of polarity. It is because of the convection current in the iron core. If the movement is like this, the north-south direction in certain way, and if the direction is movement of like is like this, if in this case the north is along this direction, south is along this direction, in this case it will become south, it will become north. And we have seen that the Earth's polarity have changed their direction with time, and the present time is the Brunei's normal time. Over the last 0.7 million years, our Earth is having normal polarity, and this polarity is found to change with time because of the geodynamic effect at the Earth's interior. And it is confirmed that Earth is possessing those magnetic minerals within the Earth's interior, and these magnetic minerals are iron. If this would not have been there, then Earth would not have possessed this magnetic field. So, Earth core must be represented by iron, and it must be in liquid state. Besides this, the most conclusive evidence is provided by the seismic waves, earthquake waves, because these earthquake waves, they propagate all through the Earth's interior, from the focus from the place where the earthquake is originated. From that, the waves they move in all directions through the entire earth, and their time of arrival in the recording stations are observed, and those data are being analyzed in order to find out the internal structure of the earth. The waves that migrate from the focus, they are body waves, that is P and S waves, or they are surface waves. Surface waves are L and R waves, which are produced because of the interference of P and S waves, and they occur in the epicentral zone of the concerned with the earthquake, and there the maximum devastation takes place. But body wave, P and S wave, they simply pass through the body of the earth and they are received at the recording stations in different times. Here we have to remember that P wave is a primary wave which passes through solid, liquids and gas, whereas S wave is the wave, secondary wave, which passes through solids only. These two characters are studied by their time of arrival in the recording stations, which are distributed all over the globe in different parts of the earth. And the P wave velocity is greater than S wave, greater than L wave, greater than R wave. So this is the velocity of the waves, and so P wave reaches the recording station first, followed by S wave. So based upon the time of arrival of waves, the seismogram provided by the seismographs are studied, and on that basis the shadow zones are detected. Shadow zones for P and shadow zones for S, they are being detected. If this is the origin, place of the origin of the earthquake, if the epicenter will represent the 0, and on the opposite side it is 180. So the P and S waves, they are found to reach on both sides at 105 degree range, 105 degree range, P up to 105 degree from 0, because it is a sphere, earth is a sphere. So from 0 to 105 degree range, P and S waves both are found to reach, but from 105 to 145 in this zone, P is not found to reach. It is because of the presence of a liquid medium, that is outer core. So 105 to 105 zone in the Earth's surface with respect to this earthquake receives no P wave, and the entire zone from 105 to 105, this part of the Earth's surface receives no S, because S wave passes through solids, S wave does not pass through the liquids. Because the outer core is in liquid condition, that's why it is not passing through the core. So S wave is not found, so this is the S to S shadow zone. 105 to 105 is S to S wave shadow zone. 105 to 145 on one, this is the zone in which P wave is not found to reach, that is the P shadow zone. And on the analysis of this data, time of arrival of waves in the recording stations, the calculations have been made, and it is clear that the Earth is presently a layer structure with the outer core in liquid state and the inner core in solid state, and the Earth is made up of 3 layers: the crust, which is the light layer, followed by denser medium, that is middle, that is occurring in the middle, which is mantle, crust, and the innermost layer is the core, represented by nickel and iron. So this is the picture that was provided by seismic waves, because seismic waves, they So there are variation in density, and density is controlled by the velocity of the seismic waves is controlled by the density, and density is found to vary from place to place within the Earth's interior, and though that is being detected from the time of arrival of these waves in the recording stations, and thus analysis of this time of arrival of waves in the recording stations or seismographs, the estimation or the measurements have been made, or the deductions have been made with regard to the Earth's interior, and the broadly Earth is classified into crust, mantle and core. And let us see what are the mechanical layers. The mechanical layers are the lithosphere, which is rigid, solid, breakable, which goes up to a depth of 100 kilometers. Below 100 kilometers, the asthenosphere, it is somehow weak, and it goes up from 100 kilometers to 660 kilometers, it is asthenosphere. Below asthenosphere, there is mesosphere, it is hard, dense rocks. It goes up to 2900 kilometers depth from 660 kilometers, and below 2900 kilometers, the iron core is present, which is metallic core. So we can say that lithosphere, asthenosphere, mesosphere and core, they represent the mechanical layers. And if you take into account the composition wise, the Earth is present in crust, mantle and core. Crust is divided into two parts, continental crust and oceanic crust, and mantle is divided into upper mantle and lower mantle. Upper mantle is existing from 33 kilometers to 660 kilometers, and lower mantle from 660 kilometers to 2900 kilometers. So this is the broad classification of Earth into crust, mantle and core. So this has been discussed here. What is lithosphere, what is asthenosphere, what is mesosphere. Lithosphere represents crust plus a part of upper mantle. It goes to, the depth goes to 100 kilometers. It is rigid, strong, breakable. Below it, there is asthenosphere. Asthenosphere from 100 kilometers to 660 kilometers. It is made up of three zones. The upper zone is very weak, and it is presenting the magma pockets. That's why the velocity of seismic waves drops in this zone. That's why it is called as the low velocity zone, LVZ. And below it there is a rigid zone from, so that I will discuss afterwards. So if we take into the mechanical layers, it is lithosphere, asthenosphere, mesosphere, and it is core. Core is made up of outer core and inner core. Outer core is in liquid state up to varying in depth from 2900 kilometers to 5.50 kilometers, and inner core, it extends from 5.50 to 6.71 kilometers. Now I will discuss about the composition layers of the Earth. So main is the crust, mantle and core. Let me discuss what is crust. Crust represents 1% of, less than 1% of the volume of the Earth and 0.4% of mass. It is extremely thin, and it is made up of two crust: continental crust, which is shale, granitic; oceanic crust, sigma or basaltic. Continental crust, this is the average crustal thickness. Continental crust is the upper crust, and it is made up of all types of rocks, igneous, sedimentary, metamorphic, which are exposed on the land surface. This layer is rich in silica and aluminum. Silica is more than 60%, with density 2.7 to 3, and the oldest continental rocks are of 4.03 billion years age. So, or it can go up to 4.2 billion years, as is found in greenstone belts. Also, the zircon in metamorphosed sedimentary rocks of Australia shows a age of 4.4 billion years, because we know the Earth originated from the Sun about 4.6 billion years back, age of the Earth. So, maximum age is shown by zircon, which is going up to 4.4 billion years. So, crustal rocks are very old, but if you take into account the oceanic crust is made up of very young rocks. The maximum age of the oceanic rocks is about 180 million years. They are made up of calcium oxide, iron oxide, magnesium oxide with silica content less than 50% or around 50%. And the oceanic crusts are, the old oceanic crusts have been destroyed in course of the evolution of the Earth from time to time, and that's why the maximum age of the oceanic crust is around 180 million years. Before that, the oceanic crust was there, but that has been destroyed during the plate motion, in which the oceanic crust has been created at the mid-oceanic ridges. And the oceanic crust is made up of SiMa, silicon magnesium rocks. It is divided into two parts, the upper SiMa, the lower SiMa, upper SiMa, and actually in between the continental crust and oceanic crust there is a break which is called as a discontinuity, with a second order discontinuity at a depth of 11 kilometers, and below it is the SiMa, silicon and magnesium rocks, and it is divided into two layers. The one layer is going up to a depth of 19 kilometers, consisting of intermediate igneous rocks, and the lower one extends from 19 kilometers to 33 kilometers, which is made up of the ultra basic rocks. So, this fact that the oceanic crusts are dense and they are devoid of continental rocks, that has been proved by the passage of L waves through the oceanic crust and the continental crust. L waves, they show a higher velocity in the oceanic surface, and that wave is low in the continental crust, and as continental crust is absent in case of oceanic crust, the L waves are higher in value, which proves that the continental crust is absent in the oceanic lithosphere, and oceanic rocks are called as oceanic tholeiids. And there are continental basalts, no doubt, but their composition is something different from the oceanic basalts. Ocean floor basalts are poorer in K, richer in aluminum compared to continental basalts, and these are known as oceanic tholeiids. And if you take into account their density, continental lithosphere or continental crust has a density 2.7 to 3, and the oceanic crust from 3 to 3.3 within this density. So this is the density of the crust, and the seismic waves, they show the velocity from 4.5 to 5 kilometers in case of S wave, and 8 to 8.2 kilometers per second for P wave. So this is about the crust. In my next video, I will discuss about the mantle. I thank you all for your patient hearing. Thank you.